So I'm going to talk about an area that I've been working in for the last 10 years or so, and a lot of other people have been working in. It's a sort of a small sub-area of theoretical computer science, but it's the sense in which it bridges any sub-disciplines is that it has many applications to other areas of computer science, and especially the parts I've been involved with have been in operating systems and architecture. So basically, what I'm going to be talking about is generally falls under the name of competitive analysis of online algorithms. So first of all, what am I talking about? So when I talk about an online problem, what I mean is a problem where you get your input in little bits, and as you receive a bit of input, you have to produce a bit of output. And your goal is to produce an output which is almost as good as it would be if you got the whole input right from the very beginning. So it's basically having to do with making decisions without future knowledge. And that kind of situation just comes up over and over again in many of the problems that we encounter. So in particular, there's a particular style of analyzing such algorithms that has become quite popular. And it's motivated by the fact that if you just take such an algorithm for such an online problem and you sort of do a worst-case analysis, just look at its absolute worst-case performance over all inputs, that number tends not to be a very useful measure of performance. An alternative would be to postulate that the input is coming from some fixed probability distribution and compute the average case performance of your online algorithm. And that is problematic because it's very difficult to come up with a fixed probability distribution that really characterizes the kind of inputs that one sees in practice. So the inputs one sees in practice tend to vary dynamically over time and across applications, and it's just difficult to come up with some fixed characterization of a probability distribution. So what competitive analysis does is it's still a worst-case measure of sorts, but it's a different kind of worst-case measure. It's focusing on what do we lose by not knowing the future. And what we do is we compare the performance of the online algorithm against the performance of the optimal offline algorithm on each input. So when I say optimal offline algorithm, I mean the algorithm that knows the entire future and does exactly the optimal thing given that knowledge. And what we'd like to say about an online algorithm is that its performance is very close to that of the optimal offline. Okay. So let me just to give you a sense of how pervasive this is, let me just mention a few examples. I'm going to be talking about online problems that come up in our field and actually other fields too. I'm going to be talking later about paging and caching, so I won't really mention that problem so much right now. But generally, paging and caching has to do with memory allocation. And in general, any resource allocation or scheduling problem, or many of the resource allocations and scheduling problems, are inherently online. You have a set of resources. You have a set of demands which are coming in for those resources. And as a demand comes in, you have to allocate your resources. And you would like to, depending on the allocation or the schedule you produce at a particular time, you may or may not screw up your opportunity to allocate resources effectively for future demands. Okay, so this comes up in processor allocation, memory allocation, network allocation, any kind of resource allocation. Load balancing is the same kind of problem. You have, let's say, jobs coming in that you want to schedule on a set of processors, and you want to balance the load across the processors. If you knew what the sizes of these jobs were, you could do a perfect balance. But if you have to schedule them as they come in, then you may do quite a bit worse than you would otherwise. Routing is the same sort of thing. That's another resource allocation problem. You're allocating bandwidth in links in a particular network. Another area that's just, you know, basically every problem is an online problem is financial optimization. So, you know, whether you're playing the stock market or you're trying to convert currency or whatever, many of those problems, you would like to be able to claim that whatever it is you do is not too much worse from what the optimal offline algorithm would do, or what you would do if you knew the future. And of course, if we had a solution for that for the stock market, you would all be incredibly happy, but we don't. Another example, dynamic data structures. Any kind of data structure where you're supporting operations over time. You would like to possibly rearrange your data structure dynamically so that the particular access patterns you're seeing will be serviced in an efficient fashion. And so, again, you'd like an online algorithm whose performance is close to offline. Final example on the slide is robot motion planning. You have a robot that's trying to reach a particular destination. The terrain is not known right up front, and as the robot moves around, it may encounter new obstacles or learn new things about the terrain. And the goal is to have this robot, reach its destination or perform its task in a fashion that is which is almost as efficient as it would if it knew the terrain ahead of time and could compute the optimal strategy. Okay. So let me sort of give a slightly more formal definition of the style of analysis that I'm going to be talking about. And this is sort of typically attributed to a paper by Slater and Tarjan in the mid-'80s, although this kind of work dates back to work on bin packing in the 60s. And so basically, we talk about the competitiveness of an algorithm. We say that an algorithm is C competitive. And basically what that means is that the cost incurred by the online algorithm A in that formula is at most C times the cost incurred by the optimal offline algorithm on that same sequence. And then there's that constant B, which is there for technical reasons, and you can just forget about it. But I should have left off the slide, but I just wanted to be correct. So what this is saying is that if the algorithm is C competitive, it says that for any input, no matter what request sequence sigma you give it, it will always be at most C times worse than the optimal offline. And we talk about the competitive ratio of a particular algorithm as being the smallest C for which the algorithm is C competitive. What is the smallest number such that you can always guarantee, no matter what kind of worst case adversary produces the input for you, that it's within a factor of C of the offline. And I heard this funny story, and I'm just going to tell it just for the hell of it, which was that I heard this from Mike Sachs, and it was a story about a woman who was in a train, and she saw two guys who were in her cabin, and they were playing a game. It seemed to be a betting game. And the one guy was holding a bag of cherries, and he would pull a cherry out of the bag, hold it in his hand, in his fist, and the other person said, "Squished." So he opened his hand and showed the cherry was not squished, and the guy paid him $1. Then the guy pulled another cherry out of the bag, so the other guy said, "Not squished." And so the guy goes like that, opens his hand, shows him a squished cherry, so the other guy paid him $1, and this went on and on and on, supposedly a true story. At some point, the guy who was pulling the cherries out of the bag left the cabin, and the woman turned to the other guy and said, "Excuse me, I'm sorry this is none of my business, but don't you see what's going on here?" And the guy said, "Well, yes, but I've lost too much money to quit." And so anyway, that's an example of an adversary who can produce an input which is very, very bad, and there's no online algorithm that will be competitive for any competitive ratio for that problem. But there are other problems for which we can make this kind of guarantee. Okay. So let me give you an example from real life, which actually is a very trivial example, but I'll give you the flavor of the kinds of ideas that go on here. And it actually turns out to model some things which come up in practice. And this is ski rental. So let's say that renting skis costs $30 and buying skis costs $300. And you're about to go skiing for the first time. So what should you do? Should you buy skis or should you rent skis? Well, you might think, I may not like skiing, so I better not buy skis right off the bat, so rent skis. And you might do that, and then you might quit or whatever. You might rent skis for the rest of your life, okay? And suppose you go skiing huge number of times. Well, barring a lot of factors that I'm ignoring, like inflation and ski models and so on, that would not be the right thing to do, because if you go skiing a very large number, if you knew how many times you were going to go skiing, then you would know exactly the optimal thing to do. If you were going to go skiing more than 10 times, then you should just buy skis right at the beginning. If you're going to go skiing fewer than 10 times, then you should just rent every time. So the two extreme strategies of always renting or buying immediately are both very bad strategies if an adversary gets to decide how many times you're going to go skiing. So, but there isn't a simple online strategy which guarantees that you won't pay too much worse than the minimum amount, and that is simply rent until you've paid the cost of buying. So that means that you rent for the first 10 times in this example, and then the moment you go skiing a 10th time, you buy skis, okay? And it's pretty easy to see that you'll never pay more than twice the minimum possible. And it's also pretty easy to show, and you can think about this over lunch if you want, that there's no other algorithm that's better in the sense of guaranteeing a smaller ratio, even if an adversary gets to decide how many times you go skiing, okay? So this is a simple example of sort of using this kind of balancing strategy to make sure that no adversary can foil you too much, and in this case, you can guarantee that you're within a factor of 2. So let me just mention this is not a completely problem that doesn't come up in computer science. Let me just give you a few examples of computer science problems that this actually models. And Larry Rudolph, who came up with this formulation as ski rental, came up with it when we were working on another problem that was actually a real computer science problem. So for example, in a shared memory multiprocessor, you might have locks that protect access to shared data, protect the consistency of shared data. So when a thread attempts to acquire a lock, it has to make a decision. Should it keep running, kind of waiting for the lock to be released, so kind of just idly using the processor and repeatedly testing the lock to see if it's been released? Or, and we call that spinning, or should we block the thread and let some other thread which is ready to run take the processor? Now, blocking the thread is kind of expensive. There's some large overhead associated with that we call the context switch overhead. It's the cost of saving the thread state, scheduling a new thread, restoring the thread state when it comes back, and so on. So this is basically exactly ski rental, the decision of how long should you spin before you block. Spinning is corresponding to renting skis here. Blocking is corresponding to buying skis. Another example is sort of a simplified variant of a problem that comes up in dynamic compilation. So you have some piece of code, and you have some variable in that code which is potentially a runtime constant. And you're asking the question, well, should I actually go ahead and, while the program is executing, stop the program, run the compiler, produce a more optimized version of this particular piece of code for this variable, which is actually a runtime constant in a particular region. And you may not even know whether it's definitely a runtime constant. You may just see as you go through this particular piece of code that very often this variable has a particular value, and it may be worthwhile to produce the more optimized version of the code. So again, executing this code in its unoptimized state, which basically means the execution time is longer, sort of corresponds to renting skis, and stopping the program, running the compiler, incurring this huge overhead in order to later gain that reduced execution time every time you run that piece, that corresponds to buying skis. There are other problems. I'm not going to explain them in any detail. For example, it comes up in cache coherence in a shared memory multiprocessor. You're trying to decide should other copies of the data be updated or should they be invalidated, and that turns out to correspond to renting versus buying skis. Yeah. And I have one more example. Yeah. This has to do with carrying IP packets or datagrams over an ATM or connection-oriented type network. And it has to do with opening up a virtual circuit, that is, reserving some bandwidth along a path between a source and a destination in a network. And again, this problem turns out to correspond to ski rental, exactly. Okay. So this principle, actually there are many other examples too. I didn't want to give a complete list, but not that I know a complete list, but I just want to give you the sense that even this trivial kind of case comes up a lot. And it has been this principle of balancing cost this way, that is avoiding the buy immediately or the rent always strategies, has been useful, and it's been empirically evaluated for a number of the problems I just mentioned and some other problems. And what was found was that, well, yes, indeed, the buy immediately or the rent always strategies are really not that good, in the sense that very often you get inputs where they're really abysmally bad decisions to make, okay? But what was interesting was that the competitive algorithm, the one I just described, so rent until you pay the cost of buying, always did pretty well. But in any given situation, it tended not to do better than the best of, or even exactly as well as the best of always rent or buy immediately. That is, always rent or buy immediately varied in which one of them was good. And the competitive strategy was a little bit better than the better of the two. Well, sorry, a little bit worse than the, well, definitely better than the worse of the two, sorry. But always, never quite as good as the better of the two. And this sort of is easily explained by sort of the following phenomenon, which is that sequences are not generated by adversaries, okay? So to take this, the skiing example, you know, basically what happens is if you go skiing once, you may not like it and you may quit, okay? And if you actually bother to go skiing a second time, it sort of suggests that you probably like it at least a little bit. You're probably not going to quit. By the time you go skiing 3 times, you're very likely to go skiing many, many more times, okay? So this suggests that, you know, being so conservative in order to guarantee this factor of 2, okay, against an adversary is not necessarily the right idea. Maybe what you should be doing is adapting to basically the probability distributions of the input patterns that you tend to observe in practice, which in this case means that maybe what you should do is rent until the 3rd trip, because people either go once or twice or they go more than 10 times, and instead of waiting until the 10th. So a more natural approach, and one that's been pursued by a lot of people, is to say, well, this adversary doesn't really exist. But as I said earlier, we can't really postulate some fixed probability distribution on inputs. So instead, what we should do is assume that there is some underlying probability distribution. We just don't know what it is. And I'll say, denote by P of I, the probability that you'll go exactly I times. So if we knew what those P of I's were, we could compute the optimal strategy. We could figure out exactly how many times we should rent until we buy. And the idea is that we'll do that computation, but we'll do it dynamically for the set of the probability distribution we observe. We'll adapt to that and perform optimally against that probability distribution. And we were able to show for this simple example of this ski rental against a distribution that you could show a better bound now than a factor of 2 compared to the optimal offline. You could show that it was, for any probability distribution, the strategy which does what's described on the slide there is within a factor of e over e minus 1, where e is the base of the natural log. That turns out to be about 1.58. And in fact, for many probability distributions, it's much better than that. Yeah. So that was sort of supposed to be an introduction to just generally what this area is about and why it might have a lot of tentacles out into other parts of computer science and maybe other areas. I'm going to talk a little bit more now about some current research directions in this area. I've already given you a sense of this move, this shift that's been taking place towards more what I call practical competitive analysis. So less adversarial, algorithms that adapt to the distribution of inputs. And I'm going to go into another example of that in more detail. And then a lot of work that's been going on has been on sort of taking the theory, applying it to practice, looking at a number of interesting problems, and I'm actually not going to spend much time talking about that. But even within the original framework, the adversarial framework, there are still interesting theoretical questions that are also being looked at that I'll maybe talk about briefly. And those are still important because we found that even understanding the right online algorithm against the worst case adversary helps us in learning, in designing algorithms that adapt to distributions. Those results have turned out to be quite helpful in practice. Okay, so what I'm going to do now is just give a more detailed example of some research in the area of paging with locality of reference. Okay. So what's the paging problem? I'm sure you all know it, but just for just to clarify, let me just define it one more time. Our memory is divided into pages. We assume that sort of our model is a two-level store of memory. We have some small, fast memory that can store K pages, and a large, slow memory that can store N pages. And basically what we want is that the pages we're accessing, we want them to be in the small, fast memory. So when a program performs a sequence of memory accesses, that translates into a sequence of page requests. And of course, we get a page fault whenever a page is requested which is not in fast memory. And a paging algorithm, which is inherently an online algorithm, has to decide which page to evict on a page fault. And the goal of this algorithm is to minimize the number of page faults that are incurred. And if we knew the future, we knew exactly what the sequence of page faults, of page requests would be, there's a well-known optimal strategy, and that is to replace the page whose next reference is furthest in the future. But unfortunately, we don't know the future. So Slater and Tarjan, in that original paper that I mentioned earlier on competitive analysis, looked at this problem, and what they were able to show is that there is no deterministic paging algorithm that can achieve a competitiveness better than K. So that means that no matter what paging algorithm you hand me, I can produce a page request sequence that will make your algorithm incur at least K times the number of page faults that the optimal offline algorithm would incur. Another thing they showed is that both first in, first out, that is, replace the page that was brought in longest ago, and LRU, replace the page that was least recently used, are K competitive. That is, within this measure, those are among the best possible online algorithms, okay? And you all know that both of those and variants thereof are used in practice. But this, again, pointed out a problem with this worst-case adversary type setting, which is that these results sort of conflict in some sense with our practical experience. First of all, in practice, we know that LRU, least recently used eviction, outperforms FIFO quite a bit. We also know that LRU incurs significantly less than K times the optimal offline in practice. And the reason for that has also been known for a long time. It's that page request sequences exhibit locality of reference. That is, when you request a page, you're very likely to re-request it soon thereafter. Okay. So this motivated some work by Board and Irani, Raghavan, and Schieber to introduce locality of reference into this competitive algorithms framework. And what they proposed was to introduce the notion of an access graph. So an access graph, which I have a stupid little example of in the corner there, is a graph where every vertex corresponds to a page that the program can reference. And the edges are how we impose the locality of reference relation. So if we're currently requesting some particular page, which is some particular vertex in that graph, then the next reference must be to one of the adjacent pages in the graph. So a graph sort of defines a set of possible request sequences, namely those request sequences which correspond to walks moving from node to adjacent node in this graph. And this is quite a reasonable idea for how to model locality of reference. So the idea would be, again, that if it were an undirected graph, it might correspond to the data structures that are being used by the program. Like, for example, if you were using a tree data structure, then it may be that the page access sequence sort of looks tree-like, okay? Or if in the directed case of a directed graph might correspond more to the flow of control inherent in the structure of a program. And they proposed that we modify this definition of competitive analysis to, it's exactly the same as before, except that instead of saying that the algorithm is within a factor of C of the performance of the offline on all possible inputs, we say that the algorithm is within a factor of C, or I've denoted it there by CA of G, for all possible inputs which correspond to walks on this particular graph, okay? So our goal is, given a graph, which we can either learn, the compiler can produce such a graph, or it can be learned dynamically at runtime, we want to come up with an optimal online paging strategy that will work well for inputs that correspond to walks on that particular graph. And they came up with a number of interesting results. For example, one of their hopes was to show that for any graph, the performance of LRU was strictly better than the performance of FIFO. And they were almost able to show that. And then in a subsequent result by Krobach and Noga, that result was actually proven. So again, what C sub LRU of G means, what is the competitive ratio of the LRU algorithm, the worst case ratio between its performance and the optimal offline for request sequences which are walks on the graph G. They also showed that LRU is optimal for axis graphs which are trees. And lastly, their major goal, a very major goal of their work was to try to come up with a universal algorithm. Again, I sort of said this already, an algorithm which takes as input this graph and produces as output the optimal paging strategy for that graph. And they came up with a very natural algorithm called FAR that they were almost able to show is best possible. It doesn't matter what the formula says exactly, but the algorithm is sort of almost the first thing you would guess. So in that picture at the bottom, you can think of the purple circles as representing pages which are in the fast memory, and the yellow circles as representing pages which are not. And the page with the square around it was the last page which was referenced. And suppose that the next page was referenced as the yellow page adjacent to that one. So which one of those purple pages should we throw out? Well, roughly speaking, the FAR algorithm says throw out the one which is furthest in the graph distance, okay? Because that sort of is trying to mimic the optimal offline strategy of throwing out the thing whose next reference is furthest in the future. If something is far away in the graph, then it can't be referenced anytime too soon. And subsequently, we were able to show that, in fact, this algorithm really was the right algorithm and to deal with a number of other cases. In particular, a case where instead of the request sequence being a walk on the graph, you could have sort of multiple fingers into the graph, and the request sequence, the next request would have to be a neighbor of one of these, of the nodes which is being pointed to, which corresponds to more of a multi-programming situation. And there have been a bunch of experimental evaluations of these kinds of algorithms, and more efficient and practical variants have been studied. And those results have been very, very promising. So this is just a small example of, moving from this sort of hardcore adversarial model to a more realistic model, and then trying to apply it to real practical situations. So actually, you can skip the next slide. Okay, so I'm just going to spend the last few minutes talking about some more theoretical directions. And as I said earlier, even within the adversarial framework, first of all, this has given us great insight for the practical work, so it's important to understand it better. But also, most of the results in the area have not really been very general. There's been this simple principle, this ski principle of kind of balancing costs, but we don't really understand in general for kind of a generic online problem how to produce the optimal online algorithm, or the one that minimizes the competitive ratio. So I'm just going to describe a general direction, which is, so the idea here first is to define a generic online problem, which we're going to call a task system. This was introduced by Board and Lineal and Sachs. So here's a kind of a generic online problem. You have a system which can be in one of n possible states, and you have a set of tasks that can be performed by the system. And for each task, depending on what state of the system you're in, there's a certain cost of executing that task, which I'm denoting there by C of ST. And for each pair, you can move between states at a certain cost, okay? So for each pair of states, S1 and S2, we might denote by D of S1, S2 the cost of moving from state S1 and S2. So now, this models a number of problems. I'll give you a bunch of examples, a couple of examples in a second, including all the ones I've mentioned so far. But the general problem here is now, if I present you with such a task system, that is, I tell you what these costs for executing the tasks in the particular states are, I tell you what the distances between states are, then you'd like to find an online algorithm that processes a sequence of tasks in an optimal fashion. So processing a sequence of tasks means moving between the states as appropriate and processing the task and incurring the costs of executing the tasks in those states. Yeah. So again, the paging is certainly an example of a task system where a state now is defined by the set of K pages which are in fast memory. The tasks are the different pages which could possibly be requested. The cost of executing a task in a particular state is 0 if that state contains that particular page, if that set contains that particular page, and is infinity otherwise because you're required to bring it in. So you have to move to a state that contains that page. Another example is linked list access. And here, so here we're looking at just a basic data structures problem where we have a linked list and we're performing accesses to elements in that linked list. So if there are n elements in the linked list, then the different states are all possible permutations, what order those elements are in the list, okay? And the tasks we may perform are accessing the different elements in the list. So if we want to access element X, then we're going to have to march down the list until we find the element X in the list. So our cost will be sort of the depth of X in the list. And we can also move from state to state by exchanging adjacent elements in the list. So we can say, for example, that exchanging a pair of adjacent elements in the list will cost 1 unit. So I just wanted to mention, as sort of an aside, a lovely and kind of amazing result about this particular problem, the linked list problem, that's also by Slater and Tarjan. And what they showed was that there's a very simple online algorithm for dynamically updating a linked list that is very close to optimal offline. So in particular, the online strategy they propose is the move to front strategy. That is, whenever you access an element in the list, move it to the front of the list, okay? And what they were able to show is that if you take an algorithm which knows ahead of time the sequence of accesses that will be performed on the list, dynamically rearranges the list optimally for that sequence of accesses, then even with that incredible amount of extra knowledge, this move to front heuristic is always within a factor of 2 in terms of its total cost. And actually, the more you think about it, the more you can become surprised by this. It's pretty amazing because this optimal offline strategy, there isn't even an efficient algorithm known for computing it. It's a pretty complicated beast, actually. Okay. Another example of a problem that's modeled by this general task system, and again, as I was trying to indicate, it's a very generic kind of thing, is the K-server problem. So here you have a set of points, okay, and you have K servers which are sitting at K different points in this space. And requests arrive at various points, and whenever you have a request, you have to move a server to that point that was requested. And your goal is to move those servers in such a way that you minimize the total movement of all the servers. And as an example, that black bar on the bottom, of course, is supposed to correspond to a disk. And if you have, for example, a 2-server problem, those 2 servers could be the heads, which you need to, when you access data, move to the location where that data is stored. Okay? So if those 2 arrows correspond to the where the servers are currently at in this space. And suppose we have a bunch of requests to those points which are marked in blue and green, okay? Then it's not so obvious. I mean, you have to be careful about what you do. So for example, a greedy strategy, which is to, in this case, you would move, let's say you had a request at the blue square. So you would move the closer one of the 2 arrows to the blue square, okay? Then let's say you had a request at the green point, okay? Then again, that one that you just moved would be closer, so you might move that. And then suppose you had a request at the blue point again, so you might move the same one. And if you kept requesting back and forth between the blue and green, if you just did a greedy thing and tried to minimize your cost for that particular time, you would keep paying for that motion between the blue and the green point. But in this case, it would be much better to move both servers over and have one server sitting at the blue point, one server sitting at the green point, and you would never have to pay any additional cost after that. So it's not so obvious, really, how to solve this problem. And there's a great solution to the problem, which is on the next slide, and I'm tempted not to explain it to you because I don't think I'll be able to do it in my 2 minutes that I want to spend on this. So anyway, it's a really cool idea. Why don't you ask me later if you're at all interested? And why don't you go to the next slide? And basically, we're currently I'm working with students Craig Anderson and Chris Hildrum, and also with Mike Sachs. We're currently trying to understand this great algorithm, which I didn't tell you about, which is very, very interesting, is we're currently trying to figure out for what classes of task systems is that algorithm the right algorithm. And there's evidence to suggest that for a large class of task systems, it is the right algorithm. And that would be very nice because it would be a step towards a kind of a general theory of, what the right online algorithm is. Let's go to the next slide. Okay, so in conclusion, there are numerous problems in this area. It spans sort of certainly all, they come up in all areas of computer science. We know some things about them, but many of these problems are not fully understood yet. In particular, there are very few general principles for design of competitive algorithms. And these adaptive strategies show really a lot of promise. And it is a great area for bridging the gap between theoretical computer science and other parts of computer science. And I'm also working on a problem I'm really excited right now on that's in this category. It has to do with web caching and tried to place a bunch of caching servers out in the web so that, when all of us try to access the Princess Diana webpage, we don't have to wait too long. So, or the Mother Teresa one.
In all your applications, you didn't mention one which is close to my heart, which are robotic agents. And it seems to me that I and many others are very much worried about cooperative and competitive agents. And we have been looking at some game theoretic models. Could you please comment how the game theoretic models, which are continuous, I realize, and you deal with discrete representation, how do they relate to each other?
Yeah, it's a somewhat different line of attack, certainly the game theoretic models, and I'm not sure exactly how to explain the relation, but they're definitely, certainly the performance measure is quite different. But there is a very close relation, and I guess I can't do a very good job of answering that question. But I could say that your problem area, though, has been studied in our literature as well. I just didn't mention it.
Yes. When you have the graph, and you construct the graph from a dynamic, either dynamic allocation or running the program, is that still an online algorithm? And even when you do the graph, the compiler does the graph, it seems to me that still doesn't have the properties of an online algorithm because you know something about the future.
Well, I'm only using what I've seen so far, okay, in order to construct this graph. So I will be dynamically varying this graph based on future knowledge. And you could easily construct a graph. So in a situation where you can construct a perfect graph right at compile time, things become a little bit easier, but even there's still the online aspect of not knowing what kind of traversal you'll make on this particular graph, okay? So I think at both ends you still have quite an online situation in that the graph itself is varying dynamically, and also the walks on the graph are sort of being generated in an online fashion.
My question relates to that. My name is Marieta Cedilnik. I'm from Columbia, Maryland. When you generate this graph dynamically, I would expect that through time this graph would become very big. Almost all points would get connected to each other, and so you lose that power with that. So I was wondering if you let some of those connections die over time.
Definitely. If you don't do that, as you point out very correctly, all hell breaks loose.